chapter 12. Last time we started talking about, trying to remember there. Last time we talked about activation energy and the effect of temperature on the rate. We also then got into really mechanisms there towards the end. Remember, mechanisms are essentially sort of plausible pathways or explanations as to how a reaction sort of occurs. Again, it doesn't necessarily mean that it always occurs that way, but it's a plausible sort of set of reactions of how we anticipate a particular reaction would occur, with the idea that not all reactions will go from directly reactants to products. When we look at the overall reaction, it may involve a set of individual reactions, and in terms of mechanisms, those are what are referred to as elementary steps. And when you add up all these elementary steps, it sort of brings you to the overall reaction that you're sort of looking for there in that particular instance. Now, we also saw that in sort of mechanisms, we also find some things that are sometimes referred to as intermediates. And that's sort of the basis, for example, of mechanisms, is this idea that when we sort of observe a particular reaction taking place, perhaps we can detect the presence of a certain, say, molecule or compound, but yet we don't really see that compound represented in the overall reaction. And again, that would imply that, again, this reaction perhaps doesn't happen from one step directly to the other, that there's multiple steps that occur. So these intermediates are things that are sort of produced early on in the mechanism, but important for it to be an intermediate is it needs to be completely used up by the end of the mechanism. And that means that you do not see it sort of represented there in the overall reaction. So, for example, N2O2, I think, was one of the examples there we saw at the very beginning. That N2O2 was produced early on. By the time the reaction was sort of done, it was used up. How do we know if sort of a mechanism is, a good mechanism in that sense, or maybe a bad mechanism? Well, there's really kind of a couple main things that you want to look at, as we talked about, in terms of determining whether or not this mechanism could possibly be correct. The first one's a pretty simple one. You pretty much need to just add up all the steps in the mechanism. So every step that's sort of listed there in the mechanism, you basically add them together. When we add reactions together, as we talked about and did the other day, pretty much anything that's on opposite sides of the arrow will cancel or reduce down. And then pretty much everybody that's on the left-hand side of the arrows stay on the left-hand side that didn't get canceled out. Everybody that didn't get canceled on the right-hand side of the arrows stay on the right-hand side of those arrows. And when you add up all the steps, if it does pretty much equal the overall reaction you're looking at, then so far that's a good mechanism. The next and sort of most important thing, or one of the most important things, is when you determine the rate law for the rate determining step, and the rate determining step is the slow step in the mechanism, it should have a rate law that matches the one that's been found experimentally. So usually in these mechanism problems, or a number of these mechanism type problems, they will in the actual problem say, hey, experimentally or observed, the mechanism or the rate law for this reaction mechanism here was whatever it is. And when you find that rate determining step, and what the rate determining step is the slow step in the mechanism, it should have a rate law that matches perfectly to the one that was observed. And then it would be a good mechanism. So if either of those two things really don't work, then it's not a good mechanism. Now, in the process of sort of proving it, like we did on the last couple of examples, you will sometimes have in your rate determining step sort of the intermediate involved in your rate law. So in those cases, you oftentimes will have to use other steps in the mechanism to sort of substitute out. And usually there'll be like a reversible step or something like that that will allow you to basically substitute out for the intermediate, like we did in the couple of previous examples, and then get a rate law where, as we talked about, you could kind of compare apples to each other to make sure that they do truly match one another. Now, um, So we have that, we have that. So I think that was where we left off there. Any questions on any of those things there? Okay, so why don't you take a minute here? I think we left off on this example. You want to determine the overall reaction here. You want to also determine the rate determining step, and you want to determine the rate law and any intermediates in the following mechanism. So why don't you take a minute or two, see what you come up with, and then we'll talk about it, make sure everybody's there on the same page. That is it. So that means everything on the left-hand side will stay on the left. So we have 1 and 2 A's. We have a B2 there. And on the right-hand side of the arrow, we have 2 ABs. So based on sort of this mechanism, we would expect the overall reaction here to be that. We also sort of answered the other question, or one of the other questions, which is what are the intermediates? So in this case, obviously, it looks like we only really canceled out B in this case. And obviously it does not appear in the overall reaction, so that would obviously be the intermediate. Remember that the rate determining step, which is sometimes referred to as the RDS, is the slow step in the mechanism. So this type of mechanism problem is really nice because they essentially tell you right there that that is the slow step. So that should be the rate determining step in this particular case. And lastly, we can figure out the actual rate law in this case. Even though they did not give it to us, we do know from what we just talked about there that that is our rate determining step. That is the slow step. And remember that the rate determining step would have the same rate law as the one found experimentally, which means we can basically just write the rate law for that first step. And that should be the rate law for this mechanism here, or this reaction, which would look something like this. And I think we covered all the questions there. Any questions on how we determine any of those sort of steps there? So this is sort of a, I guess, a third type of mechanism problem, a little bit different than the other ones we did. This is one where they sort of ask you to determine all those things. Obviously, they would have to provide you that information of which step is slow, which step is fast, in order for you, obviously, to determine the rate law and the rate determining step and things like that. Any questions on mechanisms and how to deal with them?
I have a question.
Yeah.
So in this case, the rate determining step is exactly the same as step 1?
It is. So step 1 actually is the rate determining step. So in this sort of mechanism, it's proposed basically a 2-step process, basically 2 reactions. And it's going to be that first reaction basically that's going to take the longest basically for it to occur. And that's going to determine obviously the overall rate of the reaction because of that.
Okay, thank you.
You're welcome. Other questions? Okay, so obviously you need to be able to kind of answer these type of questions, do questions like we did the previous day there, proving if it's sort of a good or bad mechanism. This is obviously not like a good or bad mechanism type question, but still a mechanism type question. All right, so to finish out sort of this chapter here, we're going to talk about just catalysts a little bit. So catalysts are typically, again, substances that for the most part will increase the rate of a chemical reaction, and probably 99 times out of 100 if somebody is sort of referring to a catalyst, that's pretty much what they're talking about, is the idea that it will increase the rate of a chemical reaction. As I mentioned earlier in this chapter as well, there are some what are referred to as negative catalysts, which slow down a chemical reaction. But again, like I mentioned, probably most of the time, if people are sort of referring to a catalyst, they're sort of talking about it in the sense of it sort of making the reaction faster or speeding it up. Now, a catalyst, it's important to remember, is not a reactant and it's not a product. So this guy here is not a reactant, not a product, and it does not get used up in the chemical reaction as well. So it does not get used up. So it is sort of there to facilitate the reaction occurring faster in most cases. Usually in reactions on top of the arrow is where we see sort of the catalyst written. Sometimes they'll do something like a metal, maybe like platinum. Sometimes they may do something like an acid, like H plus, kind of like the kinetics reaction that we're dealing with in lab. Acid is sort of used as a catalyst in this particular reaction. So a lot of times on top of the arrow, you'll find those things written. So how does a catalyst sort of work to do that? Well, a catalyst, for the most part, you can think of it as, sort of finds an alternative path for that reaction to take place. So, you know, like the uh, like the old cartoon, so going up and over the hill, for example, the coyote or the roadrunner there finds the little door in the hill. It goes right through the hill instead of going up and over. So ultimately, the way a catalyst sort of works is it's able to, in this uncatalyzed sort of reaction here, it's able to lower the activation energy. So because it's able to lower the activation energy, as we can see over here in the catalyzed reaction, that's going to allow a greater proportion of molecules to kind of get to the other side quicker. Because again, just simply speaking, they don't have to go all the way up this hill to get to the other side. You can obviously get to the other side quicker, just like obviously if you were walking a giant hill versus a very, very small hill, you'd probably get to the other side a lot quicker. How does it do that? Well, it can either provide perhaps an area where, everybody could kind of come together in a more efficient fashion. Um, it may provide an environment where, it allows reaction to occur a lot quicker, something like all that extra acid in there, that H plus allows the environment to sort of, for example, pH to help in that process. Um, and it occurs a lot quicker than if, for example, these molecules were just flying around and then had to go try to find each other, rather than everybody sort of attracted to a central location, going to allow everybody to come in contact with each other a lot quicker and increase the overall rate of the reaction. So what we see is as the activation energy decreases, the rate basically will increase when we do that. So there are different types of catalysts, and kind of like homogeneous and heterogeneous type of mixtures. In a heterogeneous catalyst, basically the reactants and the catalysts are in different phases. So maybe, the reactants are gases, maybe the catalyst is a solid. And again, it allows maybe those things to sort of centralize each other near the catalyst and allow the reaction to occur a lot quicker. The Haber process for ammonia, so when N2 and H2 fly around, it is a spontaneous reaction, but it's actually a very slow reaction if you don't sort of include a catalyst to kind of make it happen quicker. The production of nitric acid, catalytic converters, for example, in our cars, we actually have two usually in most cars that have a catalytic converter. You got ones to take care of some of the carbons and other emissions happening there, sulfur type emissions as well. Homogeneous catalysts, we have reactants and catalysts, which are basically in the same sort of phase. So usually liquid, for example. So that's where we see a lot of acid catalysts and base catalysts sort of come into play. And again, basically in that sense, everybody's pretty much, kind of floating around in the solution. So again, by something like maybe an acid or a base, it provides the right sort of environment maybe for pH, and it allows these guys maybe to sort of interact with each other a lot quicker than they normally would if they were by themselves. Here's just sort of an example here. This is the Haber process, and there's my arrow that missed. Let's go to NH3, move that over there. And you can see these are the catalysts here. And again, this is sort of the catalyst. This would be, again, a heterogeneous catalyst more of a solid. We have our nitrogen, hydrogen gases that are flying around. And again, you can kind of think of it like these guys are, kind of maybe attracted over here. And it helps with them kind of breaking apart from each other. Also helps with the sort of reassembling there of our ammonia. And then it's able to release. rather than, again, these guys just flying around and hoping, kind of come contact with each other and stuff. And again, it provides sort of a platform, if you will, in this particular case, for this reaction to occur a little bit more efficient. Here's the production of nitric acid from ammonia and oxygen using a platinum wire as a catalyst, as you can kind of see here. In this multiple step type process here, we do make a number of things which are kind of helpful. We eventually get down to making some of our nitric acid in this process. We also make some important things, like we produce some of these guys, which can come through here and continue on this production. We also produce this guy, which actually then can go through a very short process to actually make some more nitric acid, which that's nitrous acid, and very quickly can kind of make some more nitric acid from that as well. So sort of an efficient process. Here's our sort of catalytic converters in our car. Again, we have a couple of ones that kind of take care of our hydrocarbons and some that take care of our nitrogen as it goes through there. Obviously, there are solid state sort of catalysts in here. Honeycombs are sometimes referred to, that has a catalyst in there, and as the obviously the exhaust, the combustion products, reactions and gases and stuff come through here, obviously it should hopefully kind of change it into some things that are not so maybe damaging to be released into the environment. All right, any questions on that there? Okay, that actually does wrap chapter 12. So we will be rolling now into chapter 13. A reminder, we are having a quiz next, I believe it is Tuesday, during lab, and it will be on chapter 12. So everything in chapter 12 is fair game. A reminder that you will not be given any formulas, but any type of constants or things like that would obviously be provided for you. All right. Again, these notes should be up there on our Canvas site, and we're now going to kind of change gears into talking a little bit about, obviously, chemical equilibrium in this chapter. Equilibrium is pretty much the giant topic of the class. So we're going to talk about, as we go through these different chapters, pretty much every single type of equilibrium you can imagine. But essentially, the good news is it's all pretty much the same in that sense. All equilibrium is pretty much, kind of the same idea, but there's a lot of slightly different things that are happening. To be truthfully honest with you, you probably won't need a periodic table, at least on this first one. If you did, it would be provided for you, to be honest with you. So, yeah. So if you did need one, it would be provided, but as odd as it may sound, you probably won't need a periodic table very much in these few couple of chapters and stuff. I know it's a chemistry class. We don't necessarily need it all the time. So let's talk about chemical equilibrium, and let's get into it, I suppose, here. There we go. All right. So the equilibrium condition, when we think about chemical equilibrium, it really does involve a certain type of reaction that we deal with. And these type of reactions are basically reversible reactions. So it really deals with these reversible reactions. And if you remember, you probably are familiar with reversible reactions. They basically can be identified by those arrows there. So we have arrows that are basically heading in both directions. So usually when we go from reactants to products, we refer to that as the forward direction. When we go from products back to reactants, that is usually referred to as the reverse direction. And when something reaches chemical equilibrium, it's an important idea to sort of remember what that means. And what that means is it doesn't necessarily mean that you have the same amount of reactants and products, like it's at equilibrium. So it must be equilibrium equal. So we must have the same amount on both sides. And that's not really what chemical equilibrium means. what chemical equilibrium means, as I spit that out, chemical equilibrium basically means what we were actually talking about in the previous chapter. It actually refers to the rate. And what it means is when something does reach that chemical equilibrium, the rate of the forward reaction will equal the rate of the reverse reaction. So what does that mean? Does that mean we get equal amounts on both sides? It doesn't necessarily mean that. It really doesn't mean that in most cases. What it means is just as quick as it goes from reactants to products, those products are going to make a U-turn, if you want to think about it that way, and go from products back to reactants. So we're kind of going back and forth at the same sort of rate. And what that means is wherever anybody is in terms of their concentrations, when it reaches equilibrium, they basically will maintain those concentrations. So, let's just say that at equilibrium, A was at 4 molar, this guy was at 2 molar, this guy was at 3 molar, and this guy was at 4 molar. When it reaches chemical equilibrium, they're pretty much going to be maintaining these concentrations because, again, just as fast as it goes this way, it's coming back that way. So there's kind of like a net, no change happening on either side. Everybody sort of locks into where they are at that point. And that's what it means when it says that the concentration of all reactants and products basically will remain constant with time because it's that rate of the forward equals the rate of the reverse. It also means that, when you look at a reaction that's happening, a reversible reaction like this, and you kind of look at the beaker, it may look like, for example, that the reaction is like over. Maybe it had a little bit of color and then it sort of changed color or lost its color and nothing much more looks like it's happening. So sort of on the on the big level, sort of the macroscopic level, it looks like, everything is done. But if we actually kind of zoomed in, super zoomed into what's happening there, sort of on the molecular level, there's a lot of activity if this was our A plus B going to C plus D. There's a lot of A and B going to C. There's a lot of C and D going back to A and B. So there's a lot of continuous activity to maintain that equilibrium. But sometimes when we sort of just look at it, it looks like, well, this reaction is done. There's not much happening at all. Nothing's happening. But again, if you kind of super zoom in, you will see a lot of activity happening. The forward reaction and the reverse reaction happening, equal to each other in terms of the rate. So that's why we say that, sort of on the macroscopic level, it looks static, like it's done. But really on the microscopic level, if we zoomed in, we would definitely expect to see a lot of activity to maintain that equilibrium. Just like in most reactions, though, if it is sort of a reversible reaction, for the most part, if we had something like this, which is our ammonia here, N2H2 going to NH3, when we start this reaction initially, pretty much this is, you could probably assume in most cases, that's pretty much all you got going on, which you could kind of see here. We have basically some H2 and some N2 that's present, not so much NH3 at the beginning of the reaction. As this reaction sort of starts here, basically the forward direction is going to pretty much dominate the reaction that's happening. And what that means is if the forward reaction sort of is the major reaction happening, that means that we are pretty much using our reactants to make our products. And that's why we see, as the reaction starts, a decrease here in the amount of reactants. We also would then expect to see sort of an increase in our product there. And that's what we see here. And at some point, we're going to build up enough product that it will want to start kind of going back the other way. And we kind of starting to get to that point, probably around here as it's starting to level out. And at some point, the concentrations of everybody is really starting to level out to a point where we hit everybody's concentration pretty much maintains at that point, right? And at that point where, we start building up this reverse reaction happening and this forward reactions happening, at some point, again, these two guys are going to equal each other. The forward direction and the reverse direction will equal each other in terms of the rate. And that is when chemical equilibrium has been reached. And it's at this point in sort of the diagram that everybody sort of locks into their concentrations where they're at. As you can see, pretty much maintains its concentration after that point all the way across here as well, and here as well for R and 2. So once that equilibrium is sort of met, that rate of the forward reaction will equal the rate of the reverse reaction. And again, everybody will basically maintain where they're at. Any questions on that? So initially here, if we look at, say, this reaction, as we would expect, we have no H2 or CO2 present. That pretty much is going to kick off the forward reaction from occurring. And again, as we start building up some of these guys, that's going to allow that reverse reaction to kick off. And again, it will continue until we do hit that forward and reverse rate being equal to each other and chemical equilibrium basically being reached. And again, that's what we see here in terms of looking at the rate of each of those, the forward and reverse. At the beginning, it's pretty much all forward reaction. As we start making those products there, we're starting to build up that reverse rate happening here. And at some point, like we've been talking about, they pretty much are now going to equal each other. And we pretty much flatline all the way across as they're equal to each other. That again is going to lock everybody in terms of their concentrations. So let's take a look at this here and see what we got going on. If we have this reaction here, what would happen to everybody's concentrations if we decided to add more water to it? So take a second or so here and think about if we had this guy that's sort of at equilibrium and we decide to add some water to it, how would it affect everybody's concentrations? So take a minute and we'll talk about it. To add more water here. In this particular case, we would be adding more water, which is over here on our reactant side. What is that going to do? Well, in terms of the CO, that should allow pretty much this forward reaction to kick off. Again, if you just think about it, right, what do we need for sort of a reaction to take place? Well, we need these reactants to find each other, right? So if we add more water, there's probably a greater chance that that water will be able to find the CO and the forward reaction would kick off. What does that mean for the CO concentration? Well, it's going to be used up, right? And we would probably expect it to go down in that case because it's going to be needed to be used to make our products. So what does that mean on our product side? Well, if the forward reaction is going to kind of kick off, we would probably expect the amount of H2 to go up and the amount of CO2 to probably go up as well, as we're making pretty much products in that case, and the forward reaction pretty much predominates. Now, that leaves us one guy, which is basically our water here. What does that mean for our water? Well, it's kind of hard to say because what we would probably see is definitely the water concentration would increase. And why would it increase? Well, it would increase because you actually artificially added it. So we would expect the amount of water to increase. But once this forward reaction starts to kick off after it increases, it's going to be reacting with the CO. And we would expect it to kind of come back down as it's reacting in that particular case. Where it ends up is kind of hard to say because you artificially added it. It might actually end up higher than what you started with because you kind of opened the lid there and dumped it in. Or it may end up less, but probably will end up higher than what you started with, just for that process that it sort of artificially went up because you did it, you added it, you took it off the shelf and basically added it. But as the reaction starts to happen in the forward direction, we should expect to see that trend of it coming back down. And again, because of that artificial adding, probably will end up a little bit higher where it started with. Any questions on that? So why don't we take a look at another one here, or the same reaction, but in this case, what would happen if we added H2? So take a second to think about what happens to everybody's concentration there if we add H2, sort of vessel there. So same sort of approach here. In this case, though, we're adding H2, which means in this case, we're actually adding a product. So we're increasing the amount of H2, which means H2 and CO2 should have a much easier time finding each other for the reverse reaction probably to be kicking off in this case. And because of that, we would need the CO2 to make our reactants heading in that left direction. And we would expect this guy to go down. Just like previously there, since the reaction that's going to be kicking off is the reverse reaction here, we would probably expect an increase here and an increase here. And for our H2, kind of a similar sort of effect should happen. Again, because you are adding it, we probably should see the H2 go up. But again, once it starts reacting with the CO2 here, we should probably see it start to come back down. And again, much like in the first example there, it may actually end up higher than it started with, again, just because it was sort of artificially added by you. Any questions on that one there? Okay. And that was the chart we kind of talked about with labels, so that's okay. So let's actually talk about equilibrium and the equilibrium constant and sort of its applications. So if we look at this reaction, N2O4 goes to 2NO2, we could write a relationship for this, which is, again, capital K. I'll make it really big for effect there. And this capital K is what is known as the equilibrium constant. Again, not to be confused with the small k that we were dealing with kinetics, which is the rate constant. So capital K, doesn't have to be that giant, is the equilibrium constant. And it's the relationship that develops in a chemical reaction that is obviously a constant value. So it is essentially calculated by taking the concentration of our products divided by the concentration of our reactants. So what do we see here? Well, the NO2 is our product, so products up on top. Here we actually use the coefficient in the balanced equation as the exponent. So that's where the 2 comes from, or the squared. Here, obviously, the exponent is 1, and that would be our reactants. And again, you don't need to write the 1, but it is basically to the first power. Equals, in this case, 4.63 times 10 to the minus 3. Not important, that number, but that's sort of a value for an equilibrium constant. What is this one sometimes referred to in general? If you have this general reaction, products over reactants, again, our coefficients in the balanced equation become the exponents. A reminder as well that when we see these brackets, that does mean concentration. And usually what that means is molarity, which is moles per liter. So that is usually what we talk about here. That is also why sometimes this equilibrium constant is described as not just K, but is sometimes described as Kc. C creatively for concentration there. So Kc is basically the equilibrium constant where you use concentration. Now, equilibrium constants are what it sounds like. They are constant values, basically that relationship of products to reactants, but they are constant for a couple of situations here. First off, they are the value that is constant for how the reaction is written. So when you see an equilibrium constant value, like when we see this number here, it is specific for exactly how this reaction is written, with the N2O4 on the reactant side, the NO2 on the product side. It is also constant for a specific temperature. As we will talk about in this chapter, the one thing and the only thing that basically affects the actual value of an equilibrium constant is temperature. So if temperature remains relatively the same, the value that you get for the equilibrium constant will basically be the same. And what that means is, for example, if we did this reaction that we're looking at here on top of the page, and let's say we did multiple experiments. So let's say in the first experiment, we started with 4 molar of our reactants. And let's say in the next experiment, we started with like 2 molar. And let's say in the last experiment, we started with like 2 molar of our reactants, maybe 3 molar of our products. As long as the temperature was the same for all 3 of those experiments, we would expect to find the same equilibrium constant value for that reaction, regardless of what we started with in terms of concentrations. So that is sometimes a concept that's very hard for people to sort of grasp, is the idea that, we sometimes think, well, I started with like 8 of this guy to begin with, and then the next reaction I started with 2. It can't come out the same, but it actually does come out the same in terms of the relationship of the ratio of products to reactants when that reaches equilibrium. Regardless of sort of what you started with in terms of concentrations, the end result is the same in terms of the ratio of products to reactions with reactants, which is our equilibrium constant. So that's sort of an important thing to keep in mind that sometimes throws people for a loop. They go, well, each of these reactions started with different amounts. There's no way the equilibrium constant should be the same for all of them. And again, it should be the same as long as you did not change the temperature. Now, if you did the same reaction with the same starting amounts at 50 degrees and 90 degrees, you would get a different value of equilibrium constant at 50 versus 90 degrees. But if you took it from 50 degrees to 90 degrees and then did a bunch of experiments at 90 degrees, starting with different amounts, as long as you kept it at 90 degrees, all the equilibrium constant values you would get at 90 degrees should be the same. And if you dropped it back down to 50 degrees and did a bunch of different experiments, all the equilibrium constants you get at 50 degrees should be the same. But the values between 50 degrees and when you changed it to 90 degrees, even though it's the exact same reaction, the equilibrium constant will be different. Any questions on that there? What else does the equilibrium constant kind of tell us? Well, a couple of things it will kind of tell us. First off, one important thing about the equilibrium constant, which might also be a little unusual for chemistry classes, is it is typically just a number, no units. So when we see an equilibrium constant value, it is typically just a number, no units associated with it. Sometimes is a good thing, I guess. But what does it tell us? Well, if we had a really large value of K, what would that mean? Well, if we just look at it mathematically approach here, in order to get a large value for K, that means I would need a larger value up on top and a smaller value over here on the bottom, right? If you take a large number divided by a small number, you get a large number. And what that would mean is if you get a large value for K, you would probably expect to mainly have products at equilibrium. What would it mean if the opposite was true, if we had sort of a small value of K? Well, the opposite would be true. If to get a small value of K, you need pretty much the opposite to occur. You need a small value up on top divided by a large value on the bottom gives you a small value. And that means that when we reach equilibrium, we would mainly expect to have reactants present. So the actual value of K is helpful in that sense. It does give us that idea of, when we reach equilibrium, would we expect to have a lot of products there? Would we expect to have a lot of reactants there based on the actual value that we see? Any questions on that there? And that's essentially what we see here. And sometimes a good question is, what is sort of considered a large value or a small value? So what we consider a large value here for equilibrium is that really big number of 1. Yeah, so anything sort of above 1 is considered large. Anything less than is considered small value. So typically when we're dealing with equilibrium constant values, if you have a negative exponent, it's probably like a small value. If you have a kind of positive exponent when you're calculating the equilibrium constant, it would be a relatively large one. So here, if we look at this at equilibrium, the reaction favors reactants or products. So if we look here at this reaction, we got like Mickey Mouse plus a couple of circles and upside down Mickey Mouse on the other side, I think. But the important thing here in terms of helping us determine that is actually the value of the equilibrium constant. So here at 25, that is considered a large value of K. And again, since K is basically products over reactants, again, our large value would indicate that we should have a lot more products than reactants. And that means that we would favor, in this case, products being formed when we reach equilibrium. Any questions on that there? So let's talk about some different types of equilibrium. There's homogeneous equilibrium. Homogeneous equilibrium, pretty much as we talked about a little bit before there, means basically everybody's in the same phase. So in this case, everybody there are gases. And we can write our equilibrium expression by taking the concentration of NO2 squared divided by the concentration of N2O4. And again, this is, as I mentioned earlier, sometimes referred to as the Kc value. C again meaning concentrations. Now, when we deal with something like in this reaction where we have pretty much all gases, when we think about gases, we also think about perhaps a different type of unit, and that would be like pressure, right? So when we think about gases, we think about pressure, PV equals nRT, for example. So we actually can write a equilibrium expression that deals with pressure versus dealing with concentration or molarity. It is done the exact same way, and that is P squared of NO2. That is the partial pressure squared of NO2, which is our product, divided by the partial pressure of N2O4 in this case. And this gives us a new type of K value to add to our very growing list that you might not be aware of, but there's going to be a lot of K values here. So that's Kc. This is going to be Kp, P for pressure, which is again very creative here. So there really is no difference in the sense of how we figure these out. They are both products over reactants. Just one is dealing with concentrations, one is dealing with partial pressures. And an important thing is, if you remember about pressures and maybe something like the ideal gas law there, the kind of the standard unit of pressure is an atmosphere, right? 1 atm or an atm. And that is typically the units that, for the most part, you should use in equilibrium problems. Later on, we're going to talk about doing some equilibrium calculations from initial calculations. And you'd usually want to make sure your pressure is in atmospheres. So just a reminder here, 1 atmosphere is 760 torr and 760 millimeters of mercury in this case, right? So, later on in equilibrium type problems, I'll mention it probably when we get there as well. you know, so you'll sometimes be given pressures in, you know, maybe torr or millimeters of mercury, bar, or some other type of unit. And they may want an answer in one of those units like torr or millimeters of mercury. But usually when you do the calculation involving pressure and sort of the equilibrium part of the calculation, which we'll talk about later in this chapter, you want to usually do it in atmospheres and then convert it back to whatever unit they're looking for. So it's important to keep that in mind as we go through it. And again, I'll kind of point it out when we get to that appropriate part for that. But usually atmospheres is sort of the unit that you want to use. Now, is the Kc and Kp in most cases the same exact numerical value? Not in most cases. It can happen, but in most cases, they're not really the same numerical value. But they do tell you the same thing. So, you know, if you have a large Kp value, you would expect still a lot of products at equilibrium. If you have a large Kc, you would also expect products, and vice versa. Obviously, if you have small values for each of those, you would expect more reactants when you reach equilibrium. So there must be a way to kind of go from one to the other, and there is. There's this formula here which allows us to go from Kp to Kc and vice versa. So let's talk a little bit about this equation here. This is Kp is equal to Kc RT delta N. So in this particular case, obviously our Kp is our equilibrium constant for pressure. Kc is our equilibrium constant for concentration. R is our gas constant, just like you use in sort of the gas law there. So 0.08206, or if you've learned the rounded number of 0.0821, you could use that as well. Temperature, just like kind of gases, right, usually needs to be in Kelvin. So again, doesn't need to be in Kelvin here. So that's a Celsius plus a 273 if you need to do that conversion. And the thing that's really important here is the delta N. The delta N is the change in the number of moles of a gas. And it is found by taking basically the product gas molecules divided by basically the reactant moles of gases there. And it is important to do that calculation correctly. So what I mean by that is, let's just say we had this reaction here to a gas goes to B gas here. When I calculate delta N, it would be our product side, which is 1, minus our reactant side, which is 2, and that is -1. And you may say to yourself, well, the difference is 1. Is the negative really important? And the answer is yes, it is really important, the negative, because mathematically speaking, you know, whatever this number is, if you take it to the 1 versus you take a number to the -1, it is different mathematically what you're doing. The -1 means basically 1 over the number, right? So, you know, it's important sometimes when people do the delta N part, they just sort of think about it, oh, well, the difference is 2 or the difference is 3. And there is a difference mathematically if the difference is 2 versus -2, or, you know, 1 versus -1, you know, or 3 versus -3, and so forth. So it's important not to ignore the negative part here, especially when you're doing the calculation part. Otherwise, you will find yourself obviously with the wrong answer. Any questions on that there? So when we look at a homogeneous equilibrium such as this, we can write an equilibrium expression for it. Again, basically doing our products over our reactants. And again, in this case, we would have acetate times H3O plus divided by acetic acid divided by water. But when we do equilibriums and things, there are certain things that really will not affect the equilibrium. And one thing are things that are pure liquids, like water. So if we have water in there, its concentration is pretty much going to remain relatively constant here, which means we do not actually include it in the equilibrium expression. And if we were to write the equilibrium expression for this reaction, this guy right here would be the correct equilibrium expression for this. Products over reactants, not including water, which is a pure liquid. As we'll talk about, there's really kind of two things that you don't include. And that are things that are a pure liquid, are a solid. So these two things pretty much do not get included in the equilibrium expression. So if you have a reaction where you've got liquid or you got a solid in there, water is a very common liquid. Again, in the liquid state, it is not included. And anything that's a solid would typically not be included as well. Again, as we talked about, there are no units associated with that. And again, just to make it clear, we could just get rid of this part of it here. And again, this is the correct one that I boxed. Is the correct way to write that equilibrium expression. Again, no units, just a number. Products over reactants do not include anything that is liquid, do not include anything that is really solid. What does that really leave us as to what should be included? Well, that leaves us pretty much two things. That leaves us things that are gases and things that are aqueous. And again, a difference between aqueous and liquid, just in case you don't remember what the difference is. The difference is if you have something that is a liquid, that is a pure liquid by itself. So that would be like if you just had water and just pure water. Something that's aqueous is usually a solution, and it's usually something that has been made by dissolving something in a liquid like water. So if you take water and sodium chloride and dissolved it together, you would get a sodium chloride solution, which would get the aqueous symbol. If you have just water by itself, it gets just the liquid symbol. Any questions on that? All right, so I want to take a couple minutes here and write both the Kc and Kp if possible for each of these reversible reactions, and we'll talk about, see what you come up with. Products over reactants. So let's take a look here on the first one. We can write our Kc, which would be, again, the concentration of our NO2. We do need to take it to the fourth because of the coefficient, times the concentration of O2. Again, the coefficient here is 1, so we don't need anything there. That's going to be divided by our reactant, which is N2O5 squared. Now, we can also do a Kp for this, as we got some gases happening here. The Kp for that first one would be pretty much the same thing, except that we would be dealing with the partial pressure to the fourth power there of NO2. Times the partial pressure of O2 divided by the partial pressure of our reactant, which is N2O5. Also need to square that one as well. Any questions on the first one there? Now, looking at the second one here, writing our Kc is going to be our H3O plus, our F minus, and our HF here. Again, we would not include this as that is a pure liquid, so it would not be part of our equilibrium expression. In addition, there are no gases there for the part B, so we would not have a Kp value or expression for that guy. Any questions on either of those?
Yes, Professor. So we include the, for the second one for part B, we include the plus and the minus charges inside of the brackets, right?
Yeah, so basically it's the brackets just means concentration, and it's the concentration of this whole thing. So that's H3O plus, so the plus goes with it. Yep. And the F minus would go with it. Yeah, so they would go in. So the only thing that would go sort of on the outside of any brackets would be a coefficient as sort of the exponent. Okay. Other questions? Okay. All right, so why don't we try one actually with some calculations here and see what you come up with. So based on this reaction, what's given to us here, we got some concentrations, some equilibrium concentrations of the CO, the Cl2, the CO, Cl2. We want to calculate actually both the Kc and Kp value. So take a few minutes here, see what you come up with. So we're looking for two answers here. What is the value for Kc and what is the value for Kp? So think about what information is given to you as to where you should start, and then you hopefully should be able to figure it out, and then we'll double check and make sure. Kc deals with concentrations, Kp deals with pressures. So it would make sense to us to probably begin with Kc, as we are not given anything about pressures, but we are given obviously something about concentrations. So starting with Kc, our Kc would be our products divided by our reactants. And in this case, since we have the equilibrium concentrations given to us, we just need to plug them in the right spots. So that's going to be 0.14 up on top. The CO is 0.012, and the Cl2 is 0.054 in this particular case. And if you do all that good stuff there, 0.14 divided by 0.012 divided by 0.0454, you get something like 216, which, since it's a chemistry class, probably should end up at 220 in terms of sig figs, since everybody over here is 2 sig figs everywhere. And that would be the value of Kc. Again here, no units involved, so you don't have to worry about the units, just a number in this case. That also would tell us that this is a fairly large number there for K value, and we would probably expect mainly products here when we reach equilibrium. Question first off on that part of the calculation. Okay. So now that we have the Kc value given to us, we can now use that formula that we saw that basically relates, Kc and Kp. And that was the formula that we just saw, which was the Kp is equal to Kc RT delta N. So why don't we start with the delta N part, which is the moles of products minus reactants. And we're talking about gases here. So this guy is a 1 minus our reactants, which is 1 gas molecule there and 1 there, which is 2. Again, important here, giving us not just 1, but giving us -1. We also need temperature, which was 74 degrees. So to convert our temperature into Kelvin, we're going to go 74 plus a 273, and that will get us a 347 Kelvin. And at this point, I think we got everything we need. So the Kp will equal our Kc value there that we calculated above. R, which is our gas constant. Our temperature there, which is 347. And again, the important part here, not just 1, but -1 here. So if we kind of clean up inside the parentheses, 0.08206 times the 347, that gets you about 2847 in here-ish. 2847,482. Again, we're going to take not to the first power, but to the -1, which basically means you're going to go 1 divided by that number, going to get you a 0.0351187, and that will be times our 220 here. And if we do that, they're going to get us a 7.7 as our Kp value. Any questions on that? If you went with the 216 number, you got 7.6, I think. Fairly close. Any questions on either of those sort of calculations?
Kp has no units either?
Yeah, no. So any equilibrium value has no units at all. So any K value that's an equilibrium constant, pretty much just a number. Other questions on that? Now, as we just saw in the previous slide, the value for Kc is 220, value for Kp is 77. And like I said before, in most cases, the actual numerical value of each of these guys are not equal to each other. And like I said, it can happen, but in most cases, they're not going to be equal to each other. But they both do tell us sort of the same thing. This is definitely over 1, which means we would expect products when we reach equilibrium. This guy as well, over 1, sort of a large value, also means we would expect in both cases that we would expect mainly products when we reach equilibrium. Any questions on either of that there? All right, one, yeah, question?
I'm sorry. I
Yeah.
did something different when I multiplied the R value by 347.
Yeah.
I got 0.0351. So I'm not sure what I did wrong, because I entered it exactly the same.
That's, I think, pretty much what I got at 0.0351. Yeah.
Oh, so the number.
I got the 0.03. I got the 0.0351 when I did the to the -1.
Oh, okay, perfect. That's what I was confused.
I got 20. I got 28.47 when I just multiplied the inside.
Yes. Okay. Sorry, I was confused. Thank you.
No worries. Yeah. Other questions? Okay. So why don't you try another one here and see what you come up with here. I get to turn the page. And also, I think it's missing on yours as well. This guy here, I believe, is the NO2. So I take a couple of minutes to see what you come up with. Here, we're actually looking for, based on the information, what is the equilibrium pressure of O2? So what is the equilibrium pressure of the O2 here? See what you come up with. Equilibrium pressures there for NO2 and NO. And we're looking for, obviously, the partial pressure there of O2 at equilibrium. So since we're all dealing with pressures, in this case, obviously, the Kp expression is probably where we want to kind of start. Again, it's going to be our product. So in this case, it would be the partial pressure squared of NO, again, for the coefficient, times the partial pressure of O2. Again, coefficient here is 1, divided by the partial pressure squared of our NO2, again, for its coefficient. And that would equal 158 in this case. And we basically just plug in what we got going. So for our NO, that is going to be 0.270. And we are going to square that. The partial pressure of O2 is what we're looking for, divided by our NO2, which is 0.4 squared. And that equals 158. We're basically going to take this to the other side and multiply it. So we do that, 158 divided by 0.4 squared. That's going to give us 0.27 squared times partial pressure of O2 will equal our 987.5. We then want to divide this guy to the other side. Obviously will cancel, giving us a partial pressure of oxygen of that is, I wrote it not very wrong. Let's see here. Come here. 987.5 divided by 0.27 squared equals that. I think I punched a number in wrong. Let me just double check real quick. And we're going to times it by 0.4 squared. Yeah, that is definitely not 987. Sorry about that. That is, I punch it in right, 25.28. Then dividing it by 0.27 squared, going to get us 347. And again, the units here would be atmospheres. We do need units because it is a pressure. So sorry about that. I think I hit the wrong number there when I punched in. So again, multiplying 0.4 squared times 158 gives us 2528. And then we'll divide it by the 0.27 squared, getting us 347. And again, atmospheres are needed in this case because this is not an equilibrium constant we just calculated, but it is a value of pressure, so we do need those atmospheres there. Question on that calculation there. All right, question on anything we've been talking about today? think this is probably a good place to stop for today. So we'll stop lecturing here. Then in lab at 11:30, we're continuing on with obviously the experiment we started on Tuesday. So you can